The Muller Breslau Principle. Welcome back. We're going to get into the Muller Breslau Principle for plotting influence lines. And so the principle basically states that the influence line for a force or moment response is given by the deflected shape of the release structure under unit displacement rotation. So what does that mean? For reactions, it means we're going to remove the support and then apply unit displacement and draw the displaced structure. For shear, we're going to release the shear at a particular point, and we're going to replace it with what I call like a fixed roller condition. And so we're going to basically just release the shear, but we're not releasing like the connectivity of the beam. And then we're going to apply unit shear displacement to the structure and then plot the deformed shape. Lastly, for the influence line for moment, we're going to release the moment. This means we're going to put in a hinge. And then at that hinge, we're going to apply a unit displacement, which because it's a hinge, it's now a moment, it's now going to be a rotation. So we'll apply a unit rotation and then draw the deformed shape. The real advantage to the principle is it provides a very quick way to determine the influence lines at a given point. And since for determinant structures, the influence lines are straight lines, it really requires little computation, and we can also use similar triangles to help us.
So what does this look like in real life? So here I have a little model of this particular bridge, so I'm going to try to draw this. So this is point A, point B. And so what's going to happen is we're going to release, for the influence line at A, it says we need to remove like the support reaction, right? So it's like I'm going to remove this, I'm going to apply a unit displacement. So I'm going to move this up a value of 1. And so when I do that, I can look at the deflected shape of the bridge. And so you see, like, if this was up at 1, this would be 0. So we can then use the geometry of the bridge to figure out, like, down over here would be a negative 0.5. And so this is going to match our expectations from our previous problem, previous example from the last video. And we can also do it for point B. So in case of point B, I'm going to take B and I'm going to move it up 1. And now you can see if this is 0 and this is 1, then out at the end at point C, that's going to be 1.5. And again, that matches our influence line for the reaction By. And so let's go ahead and put that on paper.
All right, so here in example 3, example 3 again is the same as example 2, so just keep that in mind. So I'm going to look at for the influence line at AY, and I'm going to draw in my structures if it's a whole structure. Now what I'm going to do is I'm going to erase that support at AY, and I'm going to move it up 1. If I was to do that, what would the deflector shape be? Again, if you go back to the little video with the connects pieces, you see that it just moves something like that. And now we can use similar triangles to facilitate the calculation of all of these points, right? So again, we now have the value of 1 at A, it passes through 0 at B, and then negative 0.5 at point C. Again, we then did it for the influence line BY, so I'm going to erase the support at B. I'm going to shift it up a value of 1. So if I move that up to 1, I'm locked in at 0 at point A. Then at point C, I see it's 1.5. Again, similar triangles would show I can get 0.4, 0.5 at any point of interest along the structure. For the next part, it's going to be a little bit more difficult to envision. So for the influence line for the moment at B, I need to come into point B and I need to put in a hinge. And so here I'm just going to, sketch in and I'm drawing this. And I'm want you to imagine this beam is solid, right? So we're going to put this hinge in, but then, the rest of the structure has to remain solid and straight because the influence lines for determinant structures are always straight. So I come into this hinge and I'm going to apply this unit rotation. And so that unit rotation is going to be 1. And it needs to be 1 total, not necessarily 1 on each side. So I scratched that out because it's going to be 1 total, and both between theta left and theta right. So theta left plus theta right has to equal 1. But I don't always know how much is on each side. In this case, if I think about the left-hand side, because it's a solid beam and it's supported by that pin and roller, it really can't deflect without bending. And because the influence line for the determinant structure needs to be straight, I can't apply a unit rotation on the left because that would cause bending, which is not possible with our influence line for determinant structures. And so, therefore, all of that unit rotation 1 needs to be applied to the right-hand side. So theta left is going to be 0 in this case. Theta right will be 1. If I apply a angular rotation of 1.0, I can use rigid body mechanics or rules, and basically, for small deflections, we're going to assume that the arc length is equal to the vertical distance, so that delta will be whatever my rotation is times whatever the length of that segment is. In this case, the length of the segment is going to be 10 feet. And so I take the unit rotation of 1 times 10, and that gives me delta would equal 10. And so this is like 10 feet. So just keep in mind, if I use this influence line, it's going to give me, kip feet or something as I move that load across. And because it's down below the structure, as I drew in that rotation, it's a negative 10. I drew in that rotation in the positive direction according to our sign convention. I'm now going to look at this for the influence line for shear D. And so when I do this, I'm going to, again, sketch my solid beam, but where that discontinuity is at point D, I'm going to sketch like this fixed roller condition. So I'm kind of break the beam, but I'm not going to, necessarily, I'm going to break the beam there, and I'm going to shift it back and forth and see what would happen on either side. I'm going to apply a positive shear. So on the right-hand face of the cut, positive shear is down. On the left-hand face of a cut, positive shear is up. And so if I just draw the displaced shape after this is roughly what I would get. It would shift down on the left and shift up on the right. Now I have to figure out what the value is, because total distance here is 1, but I don't know if that, it's not 1 above the axis and below, it's that total deflection. And so what I can use is for shear, the slope of these two lines, the slope on the left-hand side and the slope on the right-hand side, actually have to be the same. So I can use that fact to know that the angle there, that angle theta that I just sketched in there at point A, you can sort of see it in there. That angle theta has to be the same on that left segment and the right segment, as I have shown there. And so I'm just going to write that down for you to make sure you know theta for shear on both sides is the same. And so if that's the same, then I can use similar triangles and some other, some information about the structure to figure out what these displacements are. So this displacement on the left-hand side would be 8 feet times whatever theta is. So that's going to be delta L, 8 theta. On the right-hand side, delta R, as I have it there, is going to be 12 times theta, because it's 12 feet times theta. And I know that total here, delta L plus delta R has to equal a total of 1. And so I'm just going to run through the math there. I'm going to add those two together. So 8 theta plus 12 theta has to equal 1.0. And so then I can solve for what theta would be. So theta would be like 1 over 20. And then I can come back and solve for what delta L and delta R would be. Delta L would be 8 over 20, which is 0.4. Delta R, 12 over 20, which is 0.6. And so now I can put values on my influence line. This is going to be at a negative 0.4 on the left and then a positive 0.6 on the right. And then I can use similar triangles to figure out the value over here. And so, I do 0.6 over a distance of 12 feet, which has to be the same as, whatever that value is over a distance of 10 feet. And so I solve for x equals 0.5. I hope this is starting to make sense for the influence lines. I want to talk a little bit about the importance of why we're going, why are we doing this with this unit value. As I previously mentioned, influence lines are very important for bridges. And so one of the loading conditions in our bridge is, according to AASHTO, which is the standard for highway design in the United States, we have these trucks, and they define the AASHTO truck as, 3 point loads. The magnitudes of these point loads are 8 kips at the forward part of the truck, and then 32 kips at each of the back 2 axles. It then stipulates the distance between the first 2 axles is 14 feet, and then the back 2 axles has to be a range of either 14 to 30 feet. And you have to pick what this range is or what this value is to maximize the effect on your structure. And so how do I figure out what what is my maximum reaction at point A, Y, when this truck drives across my bridge. Well, I now have to place this truck on my bridge with multiple point loads. And so the nice part about the influence line is it allows us to easily see, where do I position this truck to cause the maximum reaction at AY? Well, obviously, if I put one of my loads right at point A, that's going to give me, the maximum value. But then do I then just, put the back load of 32 kips and then put the next load of 32 kips 14 feet away? I would want to use 14 feet because at 30 feet, right, it would be, in this case, off my structure or, at the very far end. And then I could put the 8 kips forward, but you see that 8 kips is going to be a negative value on my influence line. So that's actually reducing the magnitude of AY. And so this isn't going to create the maximum. What I would have to do in this case is consider, well, what if I flip this around, right? What if my truck was driving from the right to the left across this bridge? Now I would see that I would have those same 32 kips, but now my 8 kip load would be off to the far left, sort of off the influence line. And that's going to give me the maximum value for AY. And to figure out what this value is, I can now figure out, okay, these two 32 kip loads are going to go in here. The 132 kip load multiplies the influence line value of 1.0. That other 32 kips, well, I'm going to have to figure out what the value of the influence line at that point is. So at a distance of 14 feet from the support A, the value of the influence line is 0.3. Again, I could use similar triangles to solve this value. So in this case, it's dropping, 0.1 every 2 feet. And so at 10 feet, it's 0.5, 12 feet, 0.4, 14 feet, 0.3, all the way down to 0 at 20 feet from point A. So then I just take the magnitudes of my influence line. I take that 1 times 32 kips plus 0.3 times 32 kips. I do the math on that to solve, and I can see that in this case, with this truck running across the bridge, the maximum, absolute maximum value I could get for AY is a total of 41.6 kips. All right, so I hope you see the value of using influence lines, especially for moving loads as we design them for highways and bridges. And so I hope you enjoyed this video, and I look forward to seeing you soon.